All right, the next section that we're going to be working on today is power series, section 10.6. So a power series, it is an infinite series, and we've been talking about infinite series. So everything we know about an infinite series, the convergence tests that we've learned and have been practicing, they all apply here for power series. What is different is, well, it's illustrated in example 1. So in this case, what we're going to do is instead of just having, so imagine I put blinders onto this, and I just kind of get rid of that for a moment, pretend that doesn't exist, then this really isn't a function of x then, and what we're left over with is just a regular old series, where our coefficients a sub n could be anything. Maybe it's some sort of alternating harmonic series, something like that. So that's just a regular series. So what we're going to do now is instead of just having these real numbers, that's what these are going to be real numbers, these the sequence term, we're now going to think of, or I should say the series term, this sequence, a sub n. Now we are going to still have this, but we are going to have this term with it, x minus c to the n. Okay. So in this way, we are going to essentially create a function of x. So as an example here, without using summation notation, we can define a power series, capital F of x. So we've got 1, x minus 2 to the first power, 2 times x minus 2 quantity squared. Notice here with this 1, we technically do have this x minus 2, but it's just raised to the 0th power, so you don't notice it. So that means the coefficient is 1, and that term is 1, since it's raised to the 0th power. So these values here underlined in blue, these are the coefficients a sub n. And then underlined in red, or like here, technically, you don't see this coefficient here. That's this term here in the power series. So the number that is being subtracted, or technically, if c itself were a negative number, then x minus negative 3, this would end up looking like x plus 3. So whatever this number here is, the opposite of it, that is going to be the center of the power series. The center. Okay. So the center of a power series is important because it is where, when we talk about convergence of a power series, which we will talk about soon, what does that mean? We'll find out that every power series does converge. So for instance, if we look up here in this power series, if I supply some value of x here, so for instance, if we just plug in the value of, let's say, 2, this gives us a regular old series. That's no different than the series that we have been studying, because these are just real numbers. So this is just like a series from the previous 5 sections of chapter 10. So in the way, the fact that we are letting this value here, x, be a variable means we have a continuously varying series. So as we vary the value of x, we want to know what values of x will cause the resulting series to converge. So note here that whatever this value c is, if we plug in this value into the power series, we'll have a sub n times 0 to the n. And since 0 is this fixed number here, since we have c minus c is 0, 0, a fixed number raised to n, even as n varies, we are going to get 0 every time. So essentially, this power series is just adding up an infinite number of zeros, which does converge, and it equals 0. So an important thing here, an important takeaway, is every power series converges at its center. Now, what may happen, and what we're interested in, is although every power series converges at its center, we want to know, are there any other values of x that we could plug in and we would still have this power series converging? So this question isn't, it sort of weakens. No longer are we interested in, does this power series converge, because we know every power series converges at its center. We want to know, where else does it converge? So how can we move away from the center? How far away from the center can we move and still maintain convergence? And that's exactly what we do here in example 1. In example 1, we define this power series. And we can see that the center is 2. So if we plug in 2, we will get, in this case, we'll have 0, 0, 0. And then here we will have 1. The reason why we have this 1 here, which I should be a little bit more specific about over here, because my power series here does begin with 0, not 1. 0 to the 0 is 1 in this case. Anything raised to the 0th power, including 0, is equal to 1. So my apologies for glancing over that. So this would actually converge to whatever A0 is in this case. Okay, so we can see that this does converge. Now what we want to do is, what happens if we plug in a different value of x? We know it converges at its center, which is x equals 2. Let's just try a different value. In this case, we will have 1 plus, well, 1 plus 2 plus 3. All of these terms here become 1, and then even though they're being raised to successively larger and larger powers, 1 squared is 1, 1 cubed is 1, so on and so forth. So we really just get these coefficients, the sum of these coefficients. So 1 plus 1 plus 2 plus 3 plus so on and so forth. Now, the pattern here definitely appears to be that these numbers are increasing, so we can assume that this series, when x equals 3, diverges. And we can continue looking at different values of x, or we can actually use a test that we've already talked about, which is the ratio test. So first, what we can do here is write this series down in summation notation. So here in this case, I broke off this 1, and then I'm just going to write down a series that works for these terms. Sometimes when you have a long pattern, it's easy to come up with a closed form expression for part of the series, but maybe not all of the series. In this case, this 1 here is just a little bit tricky to capture here. So we'll have this, and then what we're going to do is treat this expression here. Oops, I want to do that in red. We'll treat this expression here as our a sub n. So a sub n is n times x minus 2 raised to the n. So in this way, this a sub n really is a function of x, if we think about it that way. Doesn't really matter what you call it, a sub n, but we know for a ratio test, we are taking this entire thing and running the ratio test on it. So we can go ahead, figure out what a sub n plus 1 is, and divide them. So that occurs right in this step right here. simplifying some things, as we've done in the past in section 10.5 for the ratio test. And one thing we want to notice here is that these two terms, n plus 1 and n, since we are working with a series, they're not going to be negative numbers. So I know that n plus 1 is positive, and I know n is positive. So the absolute value bars, they distribute when you have a quotient or a product. So these are an absolute value, this is an absolute value, and this n's an absolute value. Since n plus 1 and n are positive numbers, the absolute values have no effect on them. Absolute n plus 1 is the same thing as n plus 1. Similarly, absolute n is just n when n is non-negative. So really, the absolute value bars, they only really need to stay on the x minus 2 term. So even here, I kept them because whether I choose to write them or not doesn't really matter, but they don't have to be here because this quantity within is non-negative. So the limit of this expression here is 1 by dominating terms. And you'll notice that this x minus 2 in absolute value got factored outside of the limit. Why is that possible? Well, this limit is as n goes to some value. So really, n's cannot leave this expression. We cannot factor anything that contains an n out. But this x minus 2 is able to leave because there are no n's in that expression. So when we take a limit as n goes to infinity, that doesn't affect this quantity here. Because there are no n's in this expression is essentially a constant with respect to this limit as n goes to infinity. So we just factor that term out, take the limit of the piece that contains the n's, so we get this limits to 1, so 1 times this absolute x minus 2. So we know for the ratio test, if we want convergence, because we do know that this power series converges at its center, what we want to know is how far away from the center can we deviate and still maintain convergence. So the ratio test says that if your rho, your ratio, is less than 1, then you have convergence. So we ultimately want to examine this inequality. So this tells us the furthest that you can deviate away from the number 2 has to be strictly less than 1. So if you visualize this as a number line, so here's our number line. We're going to put the center of the power series right there. And then we can imagine walking from the center to the left and to the right just shy of 1 unit away. So I'll make this x equals 1 and x equals 3. So I'm going to put open circles here, sort of like what we have done in algebra when we're talking about domains and stuff like that. So we'll shade the interior. So here, because this inequality is a strict inequality, this means that these endpoints here, at least using the ratio test, they are not included. They're not included. Why? Well, if we were to fill them in, shade them in, that means we are saying the power series does converge at x equals 1 and at x equals 3. But what would that translate to back in our inequality? Well, that would mean we walked not just shy of 1 unit of distance away from the center, but exactly 1 unit away of distance. That means our deviation from the center was equal to 1. So that essentially changes this inequality from being a strict inequality, less than 1, to being inclusive, less than or equal to 1. But what do we know about the ratio test? The ratio test has 3 conclusions. Either your rho is strictly less than 1, and then we get absolute convergence. Rho is strictly greater than 1, and then we know for certain that the series diverges. And then the third conclusion is if rho equals 1, the ratio test is inconclusive. So this means it may or may not diverge. It's just that the ratio test isn't going to be able to tell us which one it does. So that's exactly what this says down here. So it converges for all x less than 1 unit away from the center. So we know this. Now technically what we should do is check our endpoints. So what happens when we plug in x equals 1? What happens when we plug in x equals 3? Well, if we look above here, we already did this. When we plug in 3, we notice that the series diverges. So I know that this end should not be filled in. It should remain an open circle. Now what about over here at x equals 1? We didn't do that. So let's go back up here and actually look at this expression. Or we can even just look at this expression right here. So if we plug in x equals 1, we have 1 plus the series from n equals 1 to infinity of n times negative 1 to the n. And if we run the divergence test on this series term as n goes to infinity, this limit here does not exist, which means we have divergence. So it diverges at x equals 1, so this should also remain unfilled in. So we have figured out where exactly, what range of x values our series converges. It's all x strictly greater than 1 and strictly less than 3. So this value here, which we'll talk about in more detail in an upcoming video, this number here is the radius of convergence. And this interval here that we found, so the open interval from 1 to 3, this is the interval of convergence. So the radius tells you how far away you can walk away from the center to the left or to the right and still have convergence. But the interval of convergence actually tells you when you get to all the way to the left and all the way to the right, at that very extreme final point, the furthest that the radius of convergence says you can deviate from your center, do you still have convergence there? Because it may converge, it may diverge.